No land mass to stop it. The great red spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the great red spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go Category 5 hurricanes, nothing like Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. The Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't heed the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide, giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it gets to 900 degrees, the Earth would burst into flames with all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find the planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. Lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies of Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if we were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down from the lightning happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning, just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely, that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storm bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
Humanity, ignorant in bliss. We go about our lives unaware that in the depths of space lurk invisible monsters. Destroyers powerful enough to tear apart our sun and leave our Earth a shattered, burned out ruin. You are about to enter the world of the universe's ultimate killer. We will be there when the monster is created, in the heart of a dying star. We will search for its telltale signs in the darkness of deep space. This is the story of the power that may one day destroy us all. The black hole.
There's an old saying, what goes up must come down. The thing is, it's not always true. If you throw something hard enough, it might never come down.
If something goes up fast enough, it can escape the Earth altogether. Faster still, and it can escape the immense pull of our sun, the force that holds the planets in place. fact, travel fast enough and you can even escape the pull of the billions of stars that make up our galaxy. The Milky Way.